Hi, good morning students. I am Vaishakhi Shah from LJ Institute of Engineering and Technology. In our subject Fluid Mechanics and Hydraulics, we started a chapter which is open channel flow. A flow which is open to atmosphere. The pressure acting on the flow which is atmospheric pressure, then that flow in channel which is called open channel flow. And in last lecture we derived a theory for gradually varied flow. Okay, so now in today's lecture we will discuss specific energy and specific energy curve. Now as you can see here in this diagram, bottom line is your datum. Now the distance from datum to channel bottom, considering a rectangular channel here, then distance from datum to channel bottom is Z. Okay, we already discussed this diagram in gradually varied flow theory, but we again use this diagram that distance between bottom datum of the channel, datum of the ground to bottom of the channel indicate as Z. Now here H is a height of free water, and if you are drawing a specific energy line, then the distance between free water to specific energy line is V square by 2G. So you can say that the total energy of flowing liquid in the channel per unit weight is given by the total energy equals to Z, which is your datum head, plus H, which is your pressure head, plus V square by 2G, that is your velocity head. So you can say that total energy equals to Z plus H plus V square by 2G as shown in this diagram. Total energy is Z plus H plus V square by 2G. Now Z is the height of bottom of the channel above datum, H is the depth of the liquid, and here V square by 2G. So V is the velocity of the flow. Now if channel bottom is taken as datum, so consider if bottom of the channel is taken as a datum, then Z equals to 0. So in that case your energy, that is called specific energy, if you are taking Z equals to 0, then total energy is called specific energy, where E equals to H plus V square by 2G, because Z equals to 0. Consider datum of the ground as bottom of the channel. So E equals to H plus V square by 2G. Now we are considering a rectangular channel here in which the flow is steady but non-uniform. So for that rectangular channel, imagine a rectangular channel with steady and non-uniform flow. So here Q is a discharge through the channel, is Q, B is width of the channel, H is the depth of the flow, and Q, small q, remember here this is your small q. So small q equals to discharge per unit width. Total Q is a discharge through the channel, and small q equals to discharge per unit width. So if you have to find out small q, then Q, discharge per unit width, equals to total discharge divided by width. So total discharge is capital Q divided by width B. Now here Q equals to constant, which is capital Q by V. So here Q and H are constant. Discharge and height of liquid is constant throughout the channel. Okay. So here we get small q equals to capital Q divided by B, discharge per unit width. Now we know the equation for velocity. Velocity equals to discharge upon area. Now discharge, total discharge from the channel rectangular channel is Q, capital Q, divide by area. So area of rectangular channel is width into height, width into height. So equation for area is B into H here. Okay. Now capital Q divided by small b, that is your small q. So that can be replaced by small q by h. So velocity of flow, velocity equation for velocity, which is q by h, small q by h. Clear? Now placing the value of v in equation of specific energy. Now equation for specific energy, E equals to h plus v square by 2g. So we know the equation for v. Replacing that equation, you get E equals to h plus q square divide by 2gh square. Replacing v by q divided by h. So E equals to h plus q square upon 2gh square. Now here h can be replaced by EP and q square upon 2gh square can be replaced by EK. Now what is EP and what is EK? So EP, that is your potential and potential energy of the flow. EP, that is potential energy, which is indicate as H also, and EK is your kinetic energy of flow. Which energy? Kinetic energy, and which is also indicated as V square by 2G. So your total energy E equals to EP plus EK, where EP is the potential energy of flow and EK is the kinetic energy of the flow. Okay. So now if you draw the graph between specific energy and depth of the flow, so you can take specific energy on x-axis and depth on y-axis. Here we indicate depth by h and specific energy indication is E. So the graph may be plotted like this. Here as you can see that there is a specific energy curve which is defined as a curve which shows variation of specific energy with depth of flow. Now we will see the specific energy curve here also, but first of all we know that total energy E equals to EP plus EK. So now on x-axis we are taking specific energy and on y-axis we are taking depth. Clear? So on y-axis there is a depth, on x-axis there is a specific energy. Now if you draw a line for indication of EP, then you can see here this straight line at angle 45 degree, at angle 45 degree indicates your potential energy of the flow. This straight line indicates potential energy of the flow. Now we will draw another line which indicate kinetic energy. So you can see here this curve indicates kinetic energy of the flow, kinetic energy of the flow. Clear? Now we know that total energy or specific energy is a summation of potential energy plus kinetic energy, that is EP plus EK. So now as you can see this curve, this indicates the specific energy curve. This curve indicates specific energy curve, and as we know that specific energy is a summation of potential energy and kinetic energy. So this curve is written as total energy, which is specific energy, equals to H plus Q square divided by 2gh square. Okay. So this curve, which is a combination of potential energy curve and kinetic energy curve, and this curve is called specific energy curve. So basically specific energy curve is defined as a curve which shows variation in specific energy with respect to depth. There is a change in energy, the energy changes as depth of the flow changes. Clear? So, this curve is known as specific energy curve. Okay. Now, we will see an example based on specific energy. So, let us start. In data, this is given to you a rectangular channel of 0.5 meter width. A hydraulic jump occurs at a point where depth of the water of flow is 0.15 meter and Froude number is 2.5 meter. So, determine specific energy, the critical and subsequent depth, loss of head and energy dissipation. Okay. So, first of all, in this data, rectangular channel is given to you, width which is B, width of the channel is 0.5 and Froude number given to you is 2.5. Okay. Depth of the water which is 0.15 meter. Here hydraulic jump occurs. So, let us start the example. First of all, B, that is 0.5, D1 that is 0.15 meter, B 0.5 meter, D1 0.15 meter and FR1 which is Froude number 2.5. Now, we have to find out first specific energy E1 and E2, specific energy at section 1 and section 2. Again, we have to find out HC which is your critical and D2 which is your subsequent depth. Then head loss HL and P, power dissipation. Okay. So, first of all, we know the equation for Froude number. Froude number equals to, you have to remember the equation of Froude number here. Froude number FR1 equals to V1 divided by under root G D1. So, here we know the value of V1 which is 3.033 meter per second and A1 equals to B into D1, width into depth. So, your answer for A1 is 0.05 meter square. As we know, discharge Q equals to A1 into V1. So, here answer for Q, that is 0.227 meter cube per second. Okay. If we have to find out discharge per unit width, then we know small q equals to capital Q divided by B, which is 0.455 meter square per meter cube per second. Here we know the equation for D2. So, D2 equals to D1 by 2 into under root 1 plus 8 FR1 square minus 1. So, that gives you 0.46. We know the value of D1 and FR1. So, answer for D2 is 0.46. Now, A2 equals to B into D2, B that is width and D2 that is depth. So, your answer for A2 is 0.23 meter square. Now, as we know the continuity equation. So, the continuity equation is A1 V1 equals to A2 V2. Now, we have all the values A1, V1 and A2. So, here unknown is your V2. So, you can find out V2 by placing all the values of A1, V1 and A2. So, your final answer for V2 is 0.987 meter per second. Now, firstly, specific energy. We have to find out specific energy and we know the equation for specific energy E1 equals to D1 plus V1 square by 2G and E2 equals to D2 plus V2 square by 2G. Now, we have all the values D1, V1 and G, that is 9.81. So, by placing the values in equation, your answer for E1 is 0.618 meter and answer for E2 is 0.51 meter. Clear? These are the specific energy E1 and E2. Now, second we have to find out the critical and subsequent depth. So equation, you have to remember the equation. The equation for critical depth, which is HC, equals to Q square small q. Remember, here there is a small q. So Q square by G raised to 1 by 3. Now we have the value of small q, which was capital Q divided by B. G, that is 9.81. So by placing values here, you get HC equals to 0.276 meter. HC is called critical depth. Now subsequent depth D2, we already have that answer D2, that D2 equals to 0.46 meter. Now third, head loss. We have to find out loss of head, and we know that head loss HL equals to E1 minus E2. E1 minus E2. So we know the value of E1 and E2 here, or also you can place the equation, that is D2 minus D1 raised to 3 divided by 4 D1 D2. We know the value of D1 and D2 here. So your HL, that is 0.108 meter. HL is your head loss. Okay. And fourth, we have to find out energy dissipated or power dissipated. We know the equation for power. We already studied this equation of power, and P equals to rho G Q, here there is a capital Q, into HL divided by 1000. By using this equation, you can find out power. So here rho, which is mass density, G, that is acceleration due to gravity, Q, capital Q, indicates total discharge. HL is a head loss. We already the value of HL here, divided by 1000. So by placing all the value in equation, you get a final answer for power, which is 0.24 kilowatt. 0.24 kilowatt. Clear? So in today's lecture, we studied a specific energy curve and example based on specific energy. So in next lecture, we will discuss some more topics based on the chapter open channel flow. Okay. Goodbye.